previous movie, we made sense of the information we are given in this question, and we answered questions 1 to 3. Make sure you have watched that movie first, because this movie builds on that one. In this movie and the next one, we deal with question 4. Hopefully, you have already downloaded the question from the link below and tried it yourself first. Also, remember that you can find many resources to help you learn natural and physical science topics on my website, www.learnscience.coza. Also, don't forget to subscribe to my YouTube channel. The car's engine is now switched on, and the car travels at a constant speed up the slope while there's a constant friction force of 50 newtons acting on it. Traveling in this way, it takes 15 seconds to reach C at a height of 22 meters. We're asked to calculate the power delivered by the engine to move the car from B to C. I'm going to show you 2 ways to approach this question. One focusing on force in this movie and the other focusing on energy in the next movie. You should be able to solve this question using either method, so please stay with me through both of these explanations. Being able to solve something using multiple methods increases understanding, and it gives you a way to check your answer. Obviously, in the exam, you must choose which method you prefer and use that one. And only if there's time at the end of the whole paper, you might want to return and check your answer by using the other method. First, a force perspective. We know that power is the rate at which work is done, which is the same as the rate at which energy is transferred or transformed. And work is done when force acts through a displacement. We also know that force is a vector quantity, and forces add vectorially to cause a resultant force, F net, which causes acceleration. In other words, a change in velocity and therefore a change in kinetic energy. In this particular example, we see that there is no change in velocity. The car has the same velocity at B and at C. That means there's no acceleration, which means that F net equals 0. We're going to use that fact to solve this question. How? Well, whenever we focus on forces, it's a good idea to draw a free body diagram. So let's draw a free body diagram of this 200 kilogram car. So there it is. What forces act on it? Well, we have weight down, and we know that its magnitude is mg. The mass is 200 kilograms. G is 9,8 meters per second squared. All the other forces act either parallel or perpendicular to the slope. What are these forces? Well, there's the one that we're really interested in, the force of the engine. That acts up the slope. And that is the one we're trying to find out. Then we're told that we have a constant force of friction. It must be kinetic friction because this thing is moving. Now we know that the object is moving up the slope, and kinetic friction always acts in the opposite direction to motion. So kinetic friction is acting down the slope, and we're told its magnitude, 50 newtons. And that is kinetic friction. Then we also have the normal force, which acts perpendicular to the slope. Hope that looks perpendicular. The engine exerts a force, let's call it F engine, upwards parallel to the slope. If we could find out what its magnitude was, then we'd be able to answer our question by using this equation. Power delivered by the engine equals the force exerted by the engine multiplied by the average velocity undergone, which we know is 2 meters per second. So how are we going to find the force exerted by the engine? By using the fact that the net force acting on this car is 0. So if we add this force vectorially to all the other forces on the car, we'll get 0. Forces are vectors, so if we're going to add them vectorially, we need to know their directions as well. In the case of a slope question like this one, that means that we need to know the angle that the slope makes to the horizontal before we can proceed. How are we going to find that out? So how do we get that angle? We have the information we need to do that. What information do we need? Well, let's look at this triangle here. Okay, first of all, what is this one's height? We know that the whole height from C to the reference is 22 meters. And then this height is 8,88. And so what is its height? 22 minus 8,8. What is that? 13,12 meters. Right, how does that help us? Well, we also know the length of the hypotenuse. Well, we don't know it, but it's very easy to calculate. Why? Well, we are told that this thing moves at 2 meters per second and it takes 15 seconds to move. So can you see that that distance is 30 meters? If you can't see how I got that, okay, we know that velocity is displacement per time. So displacement is equal to velocity times time. 2 meters per second times 15 seconds gives us 30 meters. So this hypotenuse is 30 meters. The height here is 13,12 meters. Which trig concept will we make use of? Can you see this is opposite, that's hypotenuse, sine theta. So we know that in this case, sine theta is equal to opposite 13,12 meters over hypotenuse 30 meters. So you can actually go and calculate, you can do this and then sine to the -1 to find theta itself. As it turns out, it's not actually even necessary, but you'll see that just now. Right, so then we know what theta is. Now, we could rearrange these vectors and draw them with a scale diagram and from that solve for the missing force's magnitude, the force exerted by the engine up the slope. But there's an easier way. So let's rather do that. What's the easier way? We resolve all the vectors into their components parallel and perpendicular to the slope. And then we can use simple algebra to add each of these directions. There's only one vector, the weight of the car, which isn't already acting either parallel or perpendicular to the slope. So we actually only need to resolve it into its components. So here we have the weight of the car, 200 times 9,8 newtons vertically downward, resolved into its components parallel and perpendicular to the slope. We can further simplify things by realizing that there are only two forces acting perpendicular to the slope, the normal force and the perpendicular component of the car's weight. And these two are going to cancel one another out, so we know that we don't need to worry about them. So we can simply focus on the forces acting parallel to the slope. So back to the weight. We need to focus on the component of the weight which acts parallel to the slope, which is W sine theta. Weight's parallel component is equal to weight sine theta. And can you see why I said we don't actually have to work out theta, because we just need sine theta. Weight times 13,12 divided by 30 is the parallel component of weight. Right, so what are we trying to do? We're trying to find out P engine. In order to do that, we need F engine. So right now, we're actually trying to find out F engine. How are we going to do that? We know that this is in equilibrium. How do we know that? Because it moves at constant velocity. Since it's in equilibrium, we know that all the forces acting on it add up to 0. There's a net force, a resultant force of 0. We can even simplify it more by just looking at the forces that act parallel to the slope, and their net force is 0. The force is acting perpendicular also, but that's not going to help us with the unknown because the unknown acts parallel. So, F net parallel forces, parallel to the slope, equals 0. Now, what are those forces? Some of them act down the slope, 2 of them do, and 1 of them acts up the slope. We specify one of the directions, let's say up the slope, to be positive. Right, so what are these forces that all add up to 0? The one up the slope, which is positive, plus friction force, a kinetic friction force, plus weight's parallel component. So, let's take F engine over to one side because that's what we're actually trying to find out. In other words, we subtract F engine from both sides, and that gives us minus F engine here, and removes it from the right-hand side, is equal to kinetic friction plus the parallel component. Now let's actually get substituting. Kinetic friction is 50 newtons, but you can't just write 50 newtons because we know that it's acting down the slope, so minus 50 newtons. And then weight's parallel component also acts down the slope, so minus. What is weight's parallel component? Well, weight is mg, 200 times 9,8, 200 kilograms times 9,8 meters per second squared. And the parallel component is W, that's weight, sine theta. And we've already seen that sine theta is that value, 13,12 divided by 30. So it's just a matter of algebra. Now we can see here, this is minus, minus, minus. We're going to sort out the minuses in a moment. We could just simply, make everything positive, if you like. Got to sort it out at one stage, so maybe that makes our calculation easier. Let's now calculate 50 plus 200 times 9.8 times, if you like, you can use the fraction function, 13.12. Make sure that you go down to the bottom of the fraction on your calculator to divide by 30, and that gives us 907,17. What have we found here? F engine, measured in newtons. Was that what we were asked? No. We're trying to find out P engine, so we haven't finished yet. P engine is equal to that multiplied by 2. F engine times average velocity. And that is what we have on the calculator, multiplied by 2. 1,814,67. What are we calculating? Watt power is measured in watts. Make sure you watch the next and last movie in this 3-part series. In that movie, we solve question 4 using energy principles rather than force, as we did here. You might find that method easier, but even if you don't, you need to make sure that you understand the concepts that we deal with in that movie so that you can answer energy-related questions.